Good day all. Today we are going to discuss module 2 conditional probability. Let's start. Here A and B are two events. A and B are two events. The probability of event A given that an event B the same sample space has happened is called conditional probability of A given B. Okay, here an event here given that the event B has happened, then the probability of event A is called conditional probability of A given B. It is denoted by probability of A given B. Okay, here the event B has happened, then what is the probability of A? It is known as conditional probability of A given B. അതായത് ബി എന്ന് പറയുന്ന ഒരു ഇവൻറ്റ് എന്ത് ചെയ്തു, നടന്നു. അങ്ങനെയാണെങ്കിൽ എ നടക്കാനുള്ള പ്രോബിലിറ്റി അതിനെയാണ് കണ്ടീഷണൽ പ്രോബിലിറ്റി ഓഫ് എ ഗിവൺ ബി. ഹിയർ ദാറ്റ് ഈസ് given that an event B has happened, then the probability of event A is called the conditional probability of A given B. The probability of event A given that an event B the same sample space has happened is called conditional probability of A given B and is denoted by probability of A given by. Okay, it is defined as, that is, probability of A given B is equal to probability of A intersection B divided by this probability of B. Okay, similarly probability of B given A is equal to probability of B intersection, that is A intersection B. Okay, B intersection is equal to A intersection B. So probability of A intersection B divided by probability of A. Okay, this is known as conditional probability of A given B and this is conditional probability of B given A. Next, show that the conditional probability satisfy all the axioms of probability. We know that there are three axioms, that is, first axiom is probability of A greater than or equal to 0. Second axiom is probability of S is equal to 1 and third is A1, A2, etc. AN are disjoint events, then probability of A1 union A2 union etc. is equal to probability of A1 plus B of probability of A2 plus etc. Okay, condition A1, A2 etc. are disjoint events. Here we prove that the conditional probability satisfy the all axioms of probability. Here the conditional probability is probability of A given B. Probability of A given B. You know that probability of A given B is probability of A intersection B divided by probability of B. Okay, here probability of A intersection B and probability of A intersection B greater than or equal to 0 and probability of B also greater than or equal to 0. Therefore, probability of A intersection B divided by probability of B also greater than or equal to 0. So, first condition satisfied. Then second, probability of sample space is equal to 1, that is probability of S given B. Probability of, instead of A here we use S. Okay, and we know that probability of A given B, what? Probability of A given B is equal to probability of A intersection B divided by probability of B. Here probability of A intersection B, that is probability of, instead of A, S, we use S. S intersection B divided by P of B. Okay, probability of S intersection B is, you know that for example S is equal to 1, 2, 3, that is sample space, and B is equal to 1, 2. So S intersection B is equal to 1 comma 2, that is B. So probability of S intersection B is equal to probability of B, okay, divided by probability of B, that is equal to 1. So axiom 2 is satisfied. And third axiom is if A1, A2, etc. A a disjoint set, then we have to prove that. That is third. That is probability of A1 union A2 union etc. given B is equal to that P of A given B is equal to P of A intersection. So here this is A, this is B. Okay, so probability of A1 union A2 union etc. intersection B divided by P of B. Okay, that is equal to we can write probability of A1 intersection B. Okay, A1 intersection B union okay, A2 intersection B etc. Okay, divided by probability of B. Okay, here A1, A2 etc. A3 are disjoint events, so we can write is equal to probability of A1, A2 etc. disjoint events. So we can write probability of A1 intersection B plus probability of A2 intersection B etc. divided by here P of B, okay, etc. So we know that the probability of A given B is equal to P of A intersection B divided by P of B. So here we can write is equal to P of A1 given B plus P of A2 given B plus etc. So this the axiom 3 is also satisfied. Okay, so therefore conditional probability satisfy all the axioms of probability. Next, multiplication theorem of probability. That is multiplication theorem of probability states. We know that probability of B given A is equal to P of B intersection, that is A intersection B divided by P of A. Okay, then what is P of A intersection B? P of A intersection B is equal to P of B given A into P of A. This is known as multiplication theorem of two events. Okay, what do you mean multiplication of two events? Probability of A intersection B is equal to probability of A into probability of B given A. Okay, is equal to probability of A into probability of B given A is known as multiplication theorem for two events. Okay, in case of three events, that is A1, A2, A3. A1, A2, A3 are three events. Then probability of A1 intersection A2 intersection A3 is equal to, we can write P of A1 into P of A2 given A1 into P of A3 given A1 intersection A2. Can prove. Okay. Proof. Right. That is P of A1 intersection A2 intersection A3 is equal to P of A1 into P of A2 given A1 into P of A3 given A1 A2. This is known as multiplication theorem of three events. Okay, proof. Okay, we know that multiplication of three events is probability of A intersection B is equal to probability of A into probability of B given A. Okay, this is multiplication theorem for two events. Okay, and we have to prove that multiplication of three events is probability of A1, A2, A3 is equal to P of A1 into P of A2 given A1 into P of A3 given A1, A2. So, therefore, P of A1 intersection A2 intersection A3 is equal to probability of A1 intersection A2 intersection A3. Okay, here this is A, this is B. Okay, using this you can write probability of A intersection B is equal to P of A into P of B given A. Here A is A1 intersection A2. So you write P of, instead of A we write P of A1 intersection A2. Okay, P of A1 intersection A2 into P of B given A. Here B is A3. So we can write P of A3 given A1 intersection A2, that is A1 intersection A2. Okay, is equal to, we know that P of A1 intersection A2 is, that is, we know that the multiplication theorem for two events, that is P of A intersection B is equal to P of A into P of B given A. Here can write probability of A1 into probability of B. Here B is A2. So A2 given A1 into this step, that is P of A3 given A1 intersection A2. Okay, this is multiplication theorem of three events. Okay, then we have to prove that multiplication theorem of n events. Multiplication theorem of n events, that is multiplication theorem of n events states that probability of A1 intersection A2 etc. intersection AN is equal to probability of A1 into probability of A2 given A1 etc. probability of AN, A1, A2 etc. AN minus 1. Okay, here we prove this theorem by mathematical induction. Okay, that is, we know that the theorem is true for n is equal to 2. Okay, then we assume that the theorem is true for n is equal to m. We assume that this theorem is true for n is equal to m. That is here m. I can write this. Okay, assume that this theorem is true for n is equal to m. That is n is equal to, okay, that is P of A1 intersection A2 intersection AM is equal to, instead of n we write m, okay, P of A1 into P of A2 given A1 etc. P of AM given A1 A2 etc. AM minus 1. Okay, A1 A2 etc. AM minus 1 means A1 intersection A2 intersection etc. intersection AM minus 1. Okay, and then we have to prove that it is true for n is equal to m plus 1. Okay, that is probability of A1 intersection A2 intersection etc. intersection AM intersection AM plus 1 is equal to probability of A1 intersection A2 intersection etc. intersection AM, okay, intersection AM plus 1. Okay, that is equal to, we know that multiplication theorem for two events, that is probability of A intersection B is equal to probability of A into probability of B given A. Here this is A, this is B. Okay, so we can write probability of A, that is probability of A1 intersection A2 intersection etc. intersection AM into probability of B given A, that is B is here, B is AM plus 1, so probability of AM plus 1 given A. Here A is A1 intersection A2 intersection etc. intersection A, that is A1 A2 etc. AM. Okay, that is equal to, we know that probability of A1 intersection A2 intersection etc. intersection AM is, that is here. Okay, it's equal to P of A1 into P of A2 given A1 into etc. That is we can write P of A1 intersection A2 intersection etc. intersection AM is equal to P of A1 into P of A2 given A1 into etc. That is P of A1 into P of A2 given A1 etc. P of this day. Okay, AM given A2 A1 A2 etc. AM minus 1 into this day, that is probability of AM plus 1 given A1 A2 etc. AM. So by the principle of mathematical induction, the theorem is true. Okay, that is okay. Here AM plus 1. Okay. By the principle of mathematical induction, the theorem is true for any positive integer n greater than or equal to 2. Okay, that's the proof. Okay.